Hi everyone, welcome back. I hope you enjoyed the desserts. So now we have two speakers. So we've got Dr. Antonio Ken Iannillo. So Antonio is a research scientist at the Interdisciplinary Center for Security, Reliability and Trust in the University of Luxembourg. He obtained his PhD in Information Technologies and Electrical Engineering at the University of Naples, Ferreira II. His research activities focus on software dependability and security, especially software verification and security assessment. His research targets include new innovative technologies such as ARM, TrustZone, and Cortex-M, Ethereum smart contracts, and ROS.
Dr. Christof is a postdoc at the Zurich Internet Information Security and Privacy Center at ETH Zurich. He obtained his PhD in computer science from the University of Luxembourg and the Technical University of Munich. His research activities mainly focus on software security, such as program analysis and automated software verification. His research currently focuses on trusted execution environments and Ethereum smart contracts. Let's welcome.
Okay. Hello, everybody. So I'm Antonio, and today we're going to discuss a bit the automated security assessment on the Ethereum smart contract with my colleague here, Dr. Torres. So, a bit of the outline. So, just a very quick condensated 101 of what is a Ethereum smart contract, what is solidity, and then we're going a bit through like the vulnerability of the smart contracts, like the most famous ones or infamous one. And then we're going through like a bit like the assessment, automated security assessment of the smart contract. And we're going to conclude with a bit of pro and cons and some like recommendation, like very personal recommendation from our side. Okay, let's start with the crash course on Ethereum. So what is Ethereum? So Ethereum is a technology that actually allows us to build application and organization, to hold assets, to transacting and communicating without any, without depending on any third-party authority. So on the base of the Ethereum, we have like the Ethereum nodes that are computers running a software called the Ethereum client. The Ethereum client is actually there to verify all the transactions in Ethereum, to guarantee then the network security and the data consistency. And they all decide, they all store like the state of the blockchain, and they communicate to each other to update this state over a consensus. And that's what we have like the blockchain. Ethereum and the blockchain is actually a database of all the transactions that is happening on the Ethereum network. And a set of transactions, when we have like a set of transactions we want to add to this blockchain, they are grouped like in a block, hence the name blockchain. Ethereum blockchain is a public blockchain. That means that we can add data to the blockchain, but we cannot remove them. So it's like forever. Once you have like a transaction in the blockchain, it's forever. In order like to change the blockchain, you always have like to hold the majority of the computing computing power in Ethereum. On top of the blockchain, we have like smart contracts. Smart contracts are simply like software. It's composed like of code and data that are stored in a specific location in the blockchain, and they're executed, they're openly accessible, so not just like a library, but more like an open API. That means that anyone like can actually call this, this function in the smart contracts. And at the end of this pyramid, we have like the apps, so decentralized application. They are like smart contracts together with the user interface that allows like to communicate on and create like a workflow and application on this decentralized network. The amazing thing about like smart contract, as I said, is they're like more open API. So actually you can create your own application without writing any smart contract. You can simply use like smart contracts that are already available on the blockchain. And this is another view on the Ethereum blockchain. As I say, like we have like the Ethereum nodes that communicate to each other, they reach a consensus, and they share and update the blockchain. When I say that they share the blockchain, it's not that they're doing like anything like special, like dividing like the blockchain among the nodes. No, it means that every single node has like his own copy on the blockchain, and they all together update that like through a consensus algorithm and protocol. Yeah. Okay. So in Ethereum, we have like two different kind of accounts. We have like the externally owned accounts, and then we have the contract accounts. The externally owned accounts are like simply like a private key that will help, that will initiate like interaction with the blockchain, and it just consists like mainly of an address and a balance. So how much Ether, that is like the cryptocurrency, the main cryptocurrency running on Ethereum blockchain. Then we have the contract account, that is actually the account that holds like also the code and the storage for a specific smart contract. A transaction is actually always initiated by an externally owned account that starts a transaction invoking like broadcasting like the information like on the Ethereum blockchain. And then when a contract like receive this transaction, it can also like initiate like the other internal transaction, but the initial transaction is always from an externally owned account. And then the contract account can have like other internal transaction to other contracts, or like simply transferring like value to another externally owned account. So how does it work like to develop and deploy like a smart contract in Ethereum? So the developer has access to high-level languages, like the most common one is Solidity. So they have like this, they develop like the source code, and then as any other software, they just like give like the source code to a compiler that is called the Solidity compiler. And the Solidity compiler create like this Ethereum virtual machine bytecode. So is a low-level language that actually is just like a string of bytes that are interpreted by a virtual machine that is called the Ethereum virtual machine, that we're going to see like a bit more about later. So, but how does it work like invoking an Ethereum smart contract? So as we said, we have the user that is initiating a transaction. That means that he give like into this transaction, he give like an address where to actually find the code of the smart contract where the function to invoke is stored. So he goes like to the Ethereum virtual machine that is like, we're going to see like is this stack-based machine that actually retrieve the smart contract bytecode and storage from the blockchain. So going from the latest block and get like the code, it starts like to run this smart contract bytecode, and then like it uses the results to update like the smart contract storage in the next block of the blockchain. It's going to save like this information in the next block of the blockchain. So as I said, the Ethereum virtual machine is a stack-based machine, so that means that has no register. So we have like three different kind of memory allocation. We can have like the stack, we can have the memory, and we can have the storage, where the storage is the only persistent one, and is like also the most costly one in terms like of gas fee. And he has like a Turing complete set of instruction, and every instruction has a gas cost. It means that every time like you want to, the Ethereum virtual machine run one of these instructions, he has like some amount of gas that is, some amount of gas that he has to spend in order to execute that particular transaction. Just going a bit on detail, what the bytecode structure would look like for a contract. So every time like we want to start, deploy like a contract on the blockchain, we have like this structure. We have like a first part that is the deployment logic. So it's executed only once. Yeah, it's executed only once when we deploy the contract, he helps like to set up all the variables of the contracts and give like the maps runtime of the bytecode to the contract address. Then we have like the runtime bytecode that is actually like the one who handles like the function call. That means that in there you have like everything that will be called over and over from the internal transaction to execute indeed like the logic of the smart contract. And includes also like some metadata, for example, like the hash of the whole code or the compiler version that was used. And we also like have like in this like initial byte string, we also have like the arguments that are used by the constructor, so by the deployment logic for initiate like the whole smart contract. Going a bit like how Solidity like compile its code, and so how actually the majority, I would say, of the smart contract deployed on Ethereum are actually organized. Let's see a bit like what a Solidity function call looks like. So we have like this string. We have like a first 4 byte that is the function hash. That is actually the identifier of the function that we want to call with that message. And then we have like the function arguments. That there is the remaining data. So as you can see, whenever like we have like a message like to the Ethereum virtual machine who's this special instruction that is the call data load that is used to read like this byte string. The first 4 bytes are used by a special part of the smart contract that is called the function dispatcher, that is the very beginning of the smart contract. It's simply like, imagine that like as a switch. Of course, like there is no switch instruction in the Ethereum virtual machine. It's more like a series of jump, and they are going to check if there exists like a function with that hash, and then it jump like to the function block to execute that specific hash. But how actually we transfer Ether, so the cryptocurrency of Ethereum, how we transfer Ether between like the different accounts. We have like 3 different ways, even though like nowadays like the last one is the most used and the one suggested by Solidity as well. So we have like the send function, the transfer function, and the call value function. So the first 2, you cannot adjust the gas, so like a bit limited. You have just like 2,300 gas limit, while like the last one you can set like how much gas you want to use for that. And the send is just like on error, it'll just like return false. On the transfer one is instead like raise an exception, throw an exception. While the call value like is simply like return false again. The call value the call is used like for call any function, and using like the value modifier, you can actually transfer also like Ether to the contract you're calling. So we are calling like one of these functions to send Ether to one of the account, and we say that we send Ether like to a smart contract, what we're interested into. By default, we have like, there is like a receive function that is executed on a call with MP data. So if you have a call just like with the value and not data on it, there is like this receive function that is used to receive like the Ether. If there is no such a function, but there is like a payable fallback function, then the fallback function will be called. I will discuss a bit about the fallback function like in the next slides. If neither the payable fallback function or the receive function exists, then it means that the contract cannot receive any Ether. So it will simply like throw an exception, and the transaction will be reverted. What we're interested more is like the fallback function. So we have to say that every contract can have like at most 1 fallback function, and the fallback function is executed on a call of the contract if none of the other function match the given function signature. That means the function dispatcher that we saw that, imagine the fallback function as the default branch of a switch. So if they cannot find any hash corresponding to a function existing, it's simply fallback to the fallback function. And is also used, as I said before, if no data is provided, so no inputs, but there is some value and there is no receive function. For example, like in this piece of code that we have here, we have like the fallback external payable function, the receive external payable function. That means that when we're going to send money without with a call value without any data, we're going like to the receive function. If you're going to put like some data, it will go on the fallback function as well. And now, like, let's go to the more interesting part. This was just like a crash course. Actually, if there is any question on this concept, I would like to take it now so that we can be sure that we all understand like the vulnerability there. But I'm pretty sure that was clear and you should already be. But please, no question is stupid question. Perfect. So let's go like with the smart contract attack. Why we're studying smart contract attack? So smart contract, like every software, can contain bugs. So developers can make mistakes. So far, like code is still developed by human being. Of course, like there is a lot of research trying to automatically develop also code. But let's say there is always like some probability that there is a mistake in this contract. But the problem with smart contract, compare like to the app on your phone, that the app on your phone can be updated. You just have a security patch and that's all. But the smart contract, no. As I said at the beginning, smart contract is immutable. That means that once we deploy that in the blockchain, you cannot change it anymore. So it's very, very important like to deploy a smart contract with the high confidence there is no critical error, critical bugs. And smart contract manage valuable assets. I mean, the whole point of like decentralized application and the Ethereum blockchain, and that we're actually holding assets that can be like cryptocurrency, can be NFT, can be everything. But anyway, it has a value, and the more value has like this token on this asset, the more interest there is from the attackers. And then source code is mostly not available. This can be a problem. That means that, of course, like as I said, like yeah, but we said that the Ethereum smart contract are like public available. Yes, if public available, but not everybody published the source code. They just published the EVM bytecode. So actually, if you have that, of course, you can reverse engineer it. You can actually like some bytecode is easy enough like to understand like that. But this put like more complexity also like on the, if you want to analyze external smart contract. And detection tool existing so far, they only highlight like bugs existence, but it's very hard like to find also like tools like that can highlight like bug locations, so exactly where the problem is. So it's like there is a lot to research like for this part. And there is like very few work, I mean, we're going to present some, but very few work like that can automatically fix bugs. So you have to manually go and fix like this bug. So, and yeah, this is the example we're going to do there. If you're like want to know like more about like vulnerabilities classification, there is like two sources that are outside there. One of that is the SWC registry, so it's the smart contract weakness classification. It's like this amazing website. I mean, it's not very. I mean, they update it time to time. They have like 36 I think now, yeah, 36 like classes of smart contract bugs. And you can actually analyze, you can actually like study them and try to understand if your code is actually vulnerable to one of these attacks. But actually more interesting is the DASP top 10 is like the top 10 like vulnerability of smart contracts that is the most common in the wild, like some of them we were going to see that, and also like the detection tool, like of course they cannot focus on all, I mean they start focusing first on like this top 10, let's say. And as you can see, like the first one is the reentrancy. So let's start with reentrancy, that is indeed like the most infamous one from the DAO attack like in 2016. So let's go like a bit through the history of the DAO attack. So I will merrily read like a bit of here. So we start in May 2016. They started like this DAO. So DAO was released, and in June 2016 they raised like over like $150 million. So it was like, at the beginning was one of the first distributed automated organization. So it was like very, he got like, it was a hype, like a lot of people was investing money in it. Then in June, the same June, we have like a blog post that tell us like, okay, there is like a possibility of a recursive callback. But 2 days after was like developer of the DAI say, okay, it's very improbable that something like that will happen, so no risk, no worry. After 5 days, like we start like to see like the attack, like something odd is going on the DAO. And then in the same day, like of course, like what was happening, they managed like to stole like $50 million through this reentrancy attack. But what is a reentrancy attack? So, for example, like we have like this piece of code this is the actual code, or like a simplified version anyway. So we have like the withdraw balance, that is the way like you withdraw money from your account. And they do like something very simple. You check the balance of your balance. So message.sender is me that I'm calling that function. So I'm checking, the contract is checking my balance. And then it's sending me like the money that I want to withdraw. So like in this call value amount, and then update my balance. Now, what happened? So transfer balance, yeah, okay. I just already said that. So let's go like walk through like the example. So we have like the DAO contract and malicious contract. So the malicious contract like start to call like the withdraw function, and you call like the withdraw balance. Then there is an Ether transfer to send the money to the caller, so I'm withdrawing my money. And here it come in play the fallback function. As we said, like the fallback function is called because we have like a call value amount with no data, and the fallback function, I manage the fallback function, so I can do whatever I want in this fallback function. What if I call again withdraw balance? You can easily see that here we are going like to call withdraw balance even before the contract actually updated my account. So I'm going again and again and again, and the contract don't even realize that I'm withdrawing more than what I actually have. And only at the end of this cycle, he updated the balance. He go like to the last line, user balance message sends, they're equal to 0. Another attack is access control. I will go also like exploiting like the fallback function. I will try to go quick, otherwise, okay. So fallback function, as we say, like when we have like no function that correspond like to what we need, to what there is in the contract, we call like this fallback function. Now, this parity wallet, they had like this brilliant idea, like, of course, like modularity is important, everybody knows it. So they have like, let's say, a front application that is the wallet contract, and then they have like a library contract, so that they can easily modify the library without modifying the whole application and just like changing like which library to point to. But what they did is they implemented the call to the library contract with the fallback function. That means, look at that, the code on the left. So the callback function, if there is some value, so if you are giving me some money, I just like deposit the money, no problem at all. If there is some data in this function, it means that we want to call some function in the wallet library. So I simply take the string and I say like, okay, go to the wallet, to the library contract and call this function. But there was no access control. Like, if you went like to a software security class 101, you know that this is like it's very straightforward to fix, but it was like, I think like was very banal, like not to see that in advance. So what they did, okay, I'm a malicious account, let's call init wallet. That is a function that only the owner is supposed to call. They call init wallet on the wallet contract. There is no init wallet in the wallet contract. They call the fallback function, and boom, they go like in the library contract and they become the owner of the library contract. And then after that, just like call kill. Is another function that there is no like in the wallet contract. They fall back, they kill the library contract, DDoS. I mean, then I was serviced. Last is like arithmetic bugs. That is like simply like when people don't think about like the size of integers, the size of the variables. So for example, like we have like unsigned integer here, super simple. It goes from 0 to 255. What happens if I do -1? The computer is just a machine. It goes like in the representation, it becomes 255. No problem at all. And that's actually what's going to happen also in smart contract. This is super small, I hope you can see. Like, we have like this check, like at the beginning. Like, okay, there is a fee amount, there is a value. I should not allow this operation if actually you want to spend more than what you have. Easy like that. Like if the fee amount plus like the value that you want to withdraw or whatever, it's greater than your balance, you should not be allowed to do this operation. Problem is, we didn't think about overflow. That means like if we manage to put like the fee set and the value to go over the maximum integer, it just becomes 0, like anyway, like a very little number. And that means that the first condition there, even if logically we know that it's not true, because it's like even greater than the maximum integer, for the machine it becomes like lower, and so we're never reverting, and we're going through the code without any problem. Yeah, and that's it like for the first part. And now I just pass over to Dr. Torres, and he will give you like an overview on the assessment of security, automated security assessment, smart contracts.
No need. Let's go to the end. Thank you for the great introduction, Antonio. So Antonio gave you basically some background on smart contracts, smart contract vulnerabilities. And now we'll just talk a little bit about how to do automated security assessment. So in general, what I will be talking about is about techniques and tools that exist already to detect bugs in smart contracts. And in general, you make this difference between static analysis and dynamic analysis. So the idea behind static analysis is that you analyze code without executing it. And the idea behind dynamic analysis is that you actually execute the code and then see what happens. So there are some advantages and disadvantages between these two techniques. So the advantage of static analysis is that it's possible to analyze the entire code because you're never really executing it. What you're doing is you're just looking at it, analyzing it. And it's super fast because you're not executing it. The disadvantage, however, is that often it's less precise because you're not really executing it, right? So you're taking assumptions while going through the code. The other thing is also that it's only suited for small programs, so programs with low complexity. The moment you have very, very complex programs, especially depending on the techniques that you're using, like for example, symbolic execution, where you actually try to represent the whole program as a graph, you will face things like the path explosion problem, for example. So therefore, you also have dynamic analysis techniques which are way more precise because you're really executing the code. So if you find a bug, then you have this confirmation that actually the bug really exists because you were able to trigger the bug by executing. And it's nice for large programs because you do not really, you don't need to create any graph representation or whatever. You don't need to care how the program is implemented. You just treat it as a black box. You send some inputs usually, and then you see how it behaves. So complexity is not really a problem anymore. The disadvantage, however, is that it's often very slow. You need to execute the program. You need to you need to create inputs. You need to wait for the execution and so on. And it's also very limited. So you need to create inputs that trigger, ideally, you need to create inputs that trigger every possible execution branch. And this is very difficult. Yes. So now we'll be talking a little bit about two different tools. One is a static analysis tool, and the other one is a dynamic analysis tools. So for static analysis tools, the most famous ones are Ethereal, Sliver, Manticore for smart contracts. And in dynamic analysis tools, you have Echidna, ILF, and SFuzz. And now we'll be talking first about Osiris, and then afterwards I will be talking about Confuzzius. So Osiris is open source. We developed at the University of Luxembourg. It's publicly available on GitHub. And you can use it to detect basically integer bugs. The idea is just to focus on integer bugs. So integer overflows, underflows, sinus bugs, conversion bugs, everything that is related to integers. So here's an overview of the architecture a little bit. So you basically give Ethereum bytecode as an input, and you get a report out of it. And it consists of three main components. The first component is called the symbolic analysis. It's based on a symbolic execution engine that was created by Louis A. And the idea is first to construct this control flow graph. So it's a representation of a program as a graph. And the idea is that you symbolically execute every single execution path in the graph, and you create basically formulas. You create equations, so you represent every execution path in the program as an equation. That's the whole idea. And then, so these equations are also called path conditions, because they basically define the condition in order to trigger this particular, that get triggered by executing this particular branch in the program, path in the program. And usually you then can use a solver to check if actually an execution path is feasible or not. Because if a solver is able to basically find a solution for these equations, then you know that the path is feasible. So the first step of the analysis is basically to create this graph and create all these path conditions. Then the second step is actually then to detect these integer errors, these integer bugs, like for example overflows or underflows. And in order to actually detect an integer bug, we first need to know what is the boundaries, what are the bounds of the integer bug, of the integer. So like maybe you know from software development, you don't just have one type of integer. You have 8-bit integers, 64-bit integers, 256-bit integers in smart contracts as well. So first we do some type inference because we need to know exactly what are the boundaries that we need to check. Then after that, what we do is, so we take back our control flow graph with all the execution paths, and we create a new constraint, a condition that basically is going to check for these integer bounds. And so what we do is we combine these two, so we have the execution path, and then we add this additional constraint that checks for integer overflow, for example, or underflow. And basically, we feed it then to the set solver, and if the solver is able to find a solution, right, to find basically a way to satisfy all the unknowns in the equations, then we know that mathematically there is a problem because the condition was triggered and is able to find a solution. So we know that there is actually an integer overflow possible. So this is how we find integer overflows. The problem is, so symbolic execution, you're executing the program symbolically. So you are basically not really executing it concretely. So you're taking a lot of assumptions, and often you have a lot of false positives. And what we do in order to reduce them is we apply something called taint analysis. It's a form of data flow analysis. The idea is that you taint, so you put a tag on a value, on a variable, and then you observe how it propagates across execution on a program. In order to understand how does it travel through execution, which locations does it touch, with which variables does it interact, with which instructions does it interact. So that's the idea. And the idea to reduce false positives that we applied here is that we said that we only want to check for bugs that actually are controllable by an attacker. So we don't care about integer bugs that are potentially possible, but cannot be actually controlled by an attacker. Then they are not really interesting bugs. So that's why we define as interesting inputs, for example, function arguments. So we tag those function arguments, we see how the data propagates. If actually they propagate and then they touch a critical arithmetic operation that triggers an integer overflow, then they are considered as interesting for us. And also, it's not just about checking the inputs, but also like where those inputs flow. I mean, after having an integer overflow, if this integer overflow is afterwards not really used by the program, then it's also not really relevant. But if this integer overflow then has an impact, for example, on storage or calling another contract, then it's relevant. So we do this taint analysis propagation also afterwards. After having identified an integer overflow, we track it further and see if it flows, for example, into storage or if it calls another smart contract. So this allows us to reduce a lot of the false positives. But still there are, of course, in the end, some false positives. Because again, a symbolic execution, static analysis, you're not really executing the program, you're just taking a lot of assumptions. Okay, so what we did is, so we developed this tool and we wanted to find out how many bugs how many smart contracts have integer bugs. So this was a study that we did in 2018 and we analyzed 1.2 million smart contracts. I think nowadays there are way more, we have 10 million of smart contracts, so this is a little bit outdated. And what we found is we found 42,000 out of these 1.2 million smart contracts to have actually integer bugs. So integer bugs can be divided in 3 classes: arithmetic, truncation errors, and sinus errors. So most of them are, of course, arithmetic. And then when we look into the arithmetic ones, we have then a division further into overflows, underflows, modulo 0, or division by 0. And then there you can see that it seems, and this was actually as anticipated, people are aware of underflows problems, right? When you have like initiated a variable with 0, and then you subtract 1, you wrap around. So people seem to be aware of this kind of problem. So that's why you see more overflows than underflows, because often people don't really think about the overflow problem, or think it's a theoretical problem, it's not really going to happen in practice. So this is also what we observed in our results. What was also interesting is at that time, so in 2018, this was a time after this whole ICO boom that happened in 2017, where everyone was creating his own ICO, making a lot of money, a lot of scams. And then basically, so what we thought is it would be nice to look at the top 500 tokens. And so we looked at them and we found that 164 out of the top 500 were vulnerable, and 2 actually had directly exploitable bugs that could be directly exploited by anyone. So here's an example of one token that actually Osiris found. And basically Osiris reported that at line 11 there's an integer underflow possible. And so this was what Osiris told us. Told us, okay, at line 11 there's an integer underflow possible. So we look at this, but we still don't know where the exact problem is. So then afterwards you need to do this reverse engineering, trying to understand how is this possible. And it's possible because of line number 7. So this condition there, the condition should be basically swapped around. So what Osiris tells us is just like the location of the bug, but probably there's some logic bug behind that integer overflow bug, and that you need to find out yourself. So this is already one of the limitations that those tools have. They tell you where the bug location is, but they don't understand how this bug was possible. So here's, for example, a screenshot of the output of Osiris. So Osiris will tell you, okay, there's an integer underflow at this particular line. And also the other 2 on top, the 2 overflow bugs, these are false positives. So these are one of the problems of these static analysis tools. They still give you a lot of false positives. And remember that I told you dynamic analysis is slow, but they are supposed to not give you any false positives, because assuming that your detectors are implemented correctly, because they actually execute the code. So you have a proof that actually when it finds a bug, that the bug is actually a bug and is not a false positive. And that's why we then decided to switch and build a dynamic analysis tool. So Confuzzius is based on fuzzing. The idea behind fuzzing is very simple. It's basically you treat a program as a black box, you generate inputs. Very dumb fuzzing is you generate random inputs, send them to the program, and then you observe the program. What does the program do? Does it crash? What is the behavior of the program? You instrument the program. But Confuzzius is a little bit smarter. So Confuzzius is a hybrid fuzzer, meaning that it combines some static analysis techniques with some dynamic analysis techniques. So here's the architecture of Confuzzius. It looks a little bit complex. It is also complex. But it basically consists of 3 components. The main component is basically these evolutionary fuzzing engine. So it applies an evolutionary algorithm. It's a genetic algorithm where you have these steps like always, the selection, crossover, and mutation. So basically you generate a population of inputs, and then you select them, and you cross them, you mutate them, and then basically they get sent, so these are called individuals, these inputs. You send them to an instrumented version of the Ethereum virtual machine. And then we execute, and then we get back a trace. And then from that trace, we learn a lot of things. So for example, how much code did we execute? Also, things like data dependencies. Also, via this trace, this is how we can detect if a particular bug was triggered or not. So in the end, then this information flows back into the evolutionary fuzzing engine, and it forms a feedback loop. So the fuzzer is not really dumb. The fuzzer learns round by round, population by population, on how to basically test more and more and more parts of the code. And in the end, you have basically then a report. So usually you give a certain amount of time or a certain amount of generations to a fuzzer, and then you just wait 1 hour, 2 hours, or like you say, like I just run 1,000 generations and then let's see the result. Okay, so just to give you a little bit more a concrete example. So this integer overflows, they are quite simple, they're quite nice, but sometimes you have some bugs that are quite complicated because they depend on multiple transactions being triggered. So it's not just enough to do one transaction to attack a smart contract. You need to combine several transactions together. So you need to, for example, call this function with this particular value, afterwards call another function, and then call another function. So the moment these attacks start becoming more complex, those symbolic execution tools, like the static analysis tools, they start having a lot of issues. So this is actually an example of a smart contract. And the problem here is, it's an old problem, it doesn't exist anymore, it's Solidity changed. But at the beginning, the way you defined your constructor in Solidity is you had to create a function that is called exactly the same way as your contract is called. So if you made a typo like here, so the name of the contract is token sale, where sale has a capital S. And so you're supposed to call the constructor function exactly the same way. But in this case, sale is with a small s. So for the compiler, this is not the constructor function anymore. This is basically a normal function. So that means that this function is then accessible after deployment as well. It's not just like accessible during deployment. And so if you know this, then an attacker can basically, so the goal of the attacker is to call withdraw function, okay, to withdraw all the funds that are in the smart contract. But the attacker needs to first set himself as the owner, because the very first check at line number 27 is checking if you, the message sender, are the owner, okay. So in order to exploit this function, you first need to call the token sale function that allows you to set yourself as the owner, and then you can call the withdraw function. So this is the attack. But you see that it already consists of 2 transactions, and actually 3, because it makes no sense to attack the contract if nobody called the buy function, because if nobody called the buy function, there's no particular asset inside the smart contract. So there are some challenges. The first challenge is this stateful exploration that we call. The bug can only be triggered if you do a specific sequence, if you call a specific sequence of functions. So for example, one example is first buy, then token sale, then withdraw. But you could also swap around. I mean, withdraw is always the last function you call. But you could also first call token sale, then you wait until someone buys, and then you call the withdraw function. The other challenge is input generation. So in this case here, at the buy, when you're fuzzing, you need to also play the victim, not just the attacker. So you also need to be able to call the buy function. So you need to be able to generate inputs sometimes that are very, very specific. So remember that a fuzzer is basically generating inputs at random. In this case, it's a very specific value, and the probability that the fuzzer is going to generate this very specific value is equals to, I mean, it's possible, but the probability is very, very, very low. So there are some smart ways. For example, you scan the code, and any constants that you see in the code, you extract them and tell them to the fuzzer. Hey, so in this case, the fuzzer would then execute constants like 42, 60, 60, 24, 1. So it sees these integers in the code, extracts them, and so on. The problem is, in order to pass this condition, you cannot just use these values, because they're dynamically computed. So there you go. You cannot use static analysis anymore to infer. So the only way to do this is to come up with a much smarter idea that can handle dynamic input values. The other challenge, the last challenge, is environmental dependencies. So smart contracts, they interact with the blockchain. So certain actions depend, for example, on the current timestamp of the block, on the block number, things like that. Things that need to be also considered. Okay, so what do we do? How do we solve these 3 challenges? Well, the first one, very simple. There's something called read after write. If you ever study data dependencies, this is a very known concept. The idea here is we execute functions, and while executing functions, we learn what kind of variables they are accessing, and if they are writing or reading from those variables. And then afterwards, we can create something called a dependency graph. So we know that, so it's read after write, right? So we know that withdraw is reading from a variable that is written in token sale. So withdraw depends, for instance, on owner. And owner is written in token sale. And buy, for example, is writing to sold, and sold is read in withdraw. So by doing this, we know that, okay, it makes no sense to generate a sequence of functions that start with withdraw. Okay? Because this is what a dumb fuzzer will do. A dumb fuzzer will generate random combinations of functions. But let's not waste our time. So let's use this read after while concept, read after write concept to generate more efficient function combinations. So using this dependency graph, we know, okay, we first need to call buy, then token sale, and then withdraw at the very end. So this is how we solve the first challenge. The second challenge is, so we try with normal fuzzing, and then we see, when we realize, because you can easily realize that the fuzzer gets stuck by seeing that, okay, no code is more being explored, no new code is being explored. So you see that, okay, the fuzzer is not being able to explore new code after 10 generations. Okay, then you know, okay, it's stuck somewhere. So what you do is you switch off the fuzzing step, and then you trigger symbolic execution, for example. Because, so you leverage inputs that you generated in the fuzzer to help solve one. So remember, symbolic execution, you have this sequence of equations that you want to solve. And in this case, this dynamic value is basically one of those unknowns. So what you do is you can fix some of the unknowns using previously generated values from the fuzzer. Those you fix, and then you leave one unknown left. And then you just call the solver, and the solver will basically try to solve and generate an input for you. Solve the equation, basically. You just treat the problem as an equation. This value is then just going to be given to the fuzzer. The fuzzer is then going to be reactivated, try, it will work, will succeed, it will pass the condition and continue exploring new code. So this is how it works. So you try fuzzing, it gets stuck, you activate symbolic execution to help the fuzzer. Afterwards, you activate the fuzzer again, and you move on. Now, challenge number 3 is this, the fact that you have an environment in blockchains. So it's not just the transactions. The environment is also important. So the way we solve this is basically we also model the environment as fuzzable inputs. So we also fuzz the block timestamp, the block number, and return values from calling functions. Okay, so this is how our fuzzer works. Of course, we also had to evaluate our fuzzer. Okay, you cannot really see the bars. Doesn't matter, you see the numbers. This is what matters. So we compared our fuzzer to 5 other tools, fuzzers and symbolic execution tools. So we divided our data set in 2, one with large smart contracts, one with small smart contracts. Of course, what is like normal, what we expected is all of the tools struggle more with large contracts because they're more complex, basically. However, the thing is, for our case, Confucius, the difference is only 10%. So on the small, we achieve 91%, and on the large contracts, we achieve on average 81%. But for example, symbolic execution tools, famous ones like Mithril, for example, they have a difference of 31%, a much bigger difference. So they really have problems with large smart contracts. And the reality is smart contracts are becoming more and more complex. I mean, those times where you just deployed a small ERC20 token are over. Nowadays, if we talk about DeFi, all those decentralized finance smart contracts, they're very, very complex. So symbolic execution nowadays is not really being used anymore. Yeah, but so for us, we can actually achieve better results. Then we compared to 2 state-of-the-art fuzzers that already existed at that time. And what is interesting is after 1 second, our fuzzer already achieves on a small smart contract data set 66%, while the competition is at 12 and 15% only. And also you can see, yeah, okay, there it's shown. So even after running, after a very long amount of time, the competition is not able to overtake us. We're still like, always have more code coverage than the competition. Then code coverage is important, and you will not find bugs if you didn't cover the code, right? But still, code coverage doesn't directly tell you about finding bugs. So we also had to evaluate our vulnerability detection mechanisms. So this is a famous data set called Smart Bugs. It's a public data set that you can use in order to test how good you're able to detect bugs in smart contracts. And Confucius is able to detect way more than the competition. And what we also saw, what we expected, is that symbolic execution tools, they have again these false positives because they are static analysis tools. And Confucius is dynamic analysis and did not report any false positives. This is the output of Confucius. On the previous example, remember this example that I gave before. So what is really nice is that Confucius tells you the line where the bug is, and it gives you the exact output sequence. So it tells you first you need to do transaction 1, call this function, then transaction 2, call this function, then transaction 3. So basically you can take this, create an exploit around it, and actually send it out and make some money. So yeah, Fuzzy is actually quite nice and convenient for developers. Because then it generates test cases and they can use this to test if they fix the bug or not. Yeah. Good. So I explained a little bit static and dynamic analysis tools. I explained a little bit the two tools that we developed and how they work, what are the differences. Now I'm just going to conclude a little bit the talk. So the talk was about automated security assessments and what is the current state of the art. So what are the advantages of using such tools is that you find quickly vulnerabilities. Very basic, simple vulnerabilities, you will easily find them. So you don't spend so much time to find them manually. There's no need to really be a security expert. I mean, if you're just a developer but never thought about security, you just run those tools and then it will tell you, look, there's a problem at this line. You also save some time and some money. So if you don't use any of these tools, right, and you just then go into a security audit, they will find a lot of things probably. And then this costs time as money. So they will write a huge report, like long calls with you. And so if you can do this, use these automated security tools already before, you reduce your costs afterwards with a security audit company. Now, the problems with automated security tools is that they only detect vulnerabilities that are known. Okay, those tools will never detect vulnerabilities that are, so zero-day vulnerabilities, game over. I mean, those tools will not be able to find them. Also, they still have a lot of false positives, especially if you use static analysis tools, which you will most likely use because they're quite quick. So running a fuzzer takes several days if you want to test it really good. So often you cannot spend so much time. Then the other thing is related to the very first problem is business logic bugs. So bugs that are really dedicated to your logic of your smart contract, those tools will never find. I mean, they're focusing on generic vulnerabilities like reentrancy, integer overflows, and so on. So you have disadvantages and disadvantages. So this brings us to recommendations. So what should you do then as a smart contract developer? You should integrate those automated security assessment tools at an early stage in your development, basically. So while testing your code, you should do this incrementally. Because I'm saying this because there's some specific bugs that actually, in order to solve them, involves changing a little bit the entire logic of the smart contract. So if you just develop your smart contract until the end, and then you run those security tools, you will realize, okay, now we need to change actually the way the whole smart contract behaves. For example, a very famous bug is this denial of service bug where you have a for loop that pays out people, and then when you realize an attacker can perform an attack by blocking these, basically. And so the idea is that you do this, you don't pay out people, generally, when you're using a smart contract. People, when they want to get paid out, they make the call to you. Okay, so it's a different thinking, a different way of thinking, different way of programming the smart contract. So this will change the whole logic of the smart contract. That's why it's important when you develop something that you use at an early stage and incrementally test your smart contract. Then it's also important to use different tools. Don't just rely on one tool, because those tools, they perform very differently. Although they are like focusing on the same type of bug, for instance, they have some different heuristics inside that they will be able to find different bugs. Also, like, those security assessment tools are nice, but they will never replace a human, like experts, security experts. So you will have to do an external audit. Actually, in some cases, it's compulsory, so you really have to. For example, very often with all those startups that use smart contracts behind the scenes, they want to put on their website that, hey, this security company audited my smart contract. But you can lower the costs with that security company if you do already some pre-assessment using some free available automated security tools. And then, yeah, finally, again, so you will still need some human to actually look at the code. I mean, you cannot just remove the human completely. Like, again, those business logic bugs, the tool will never be able to detect them. So you still need some security experts. Yeah, and I think that's basically it. So we are happy to take any questions. If you want to drop us a message after this talk, you can send us an email anytime. And yeah, we're open to take any questions.
If you'd like, you can put some questions in online as well. So we can start with the gentleman right in the middle.
can hear you from here, it's fine.
So quite a high-level question. Like, we get excited about composability of smart contracts, right? The fact that this is basically like a pseudo-open source kind of environment that you can piggyback on what everyone else has done. And I'm just wondering if you have anything to speak to the security challenges of auditing, composable smart contracts. I kind of, maybe it's just a case of, well, it gets more complicated and you have to do more of that exploration that you were talking about there. Or does the fact that you've given each of these individual contracts an audit give you any guarantee over how they behave and relate to each other? I don't know, just sort of like, would you mind saying something about the complexities that come with composability?
Yeah, sure.
Go
Okay.
ahead.
So, no, you're right. This is actually a very known problem, and it's a problem that is raising now a lot of attention because you probably heard about decentralized finance. The whole idea is that you interact with other smart contracts. You have these things like flash loans, where you can borrow money, then you can invest and do this and do this kind of combinations. And you're right. So all the security tools, including the tools that we developed, they make a lot of, they always just focus on one particular smart contract. And the bugs that they try to detect they're always just considering the context of this particular smart contract. So you're right, this is one of the problems that right now a lot of tools have, and this is an open research problem because the problem is it can be quite complex, and you don't know with which contract you will be interacting in the future. To give you one example, Uniswap, a very famous decentralized exchange, was audited, and the code was secure and everything. And then afterwards, 1 year later, came this new standard, I think the ERC 777 basically, which allowed you basically to have a callback function. So this rings a bell, reentrancy. So basically the contract itself was safe, but the problem is they started then trading tokens that implemented this callback function at the later stage, 1 year later, and this basically then allowed people to attack Uniswap smart contract. So this is one of the things, you never know about the future. You don't know what is going to be out there in the next year. So, and especially if you just look at your smart contract, it might be safe, but you don't know what kind of combinations will come in the future, and this will basically break then certain security assumptions that you made during your security audit. So you're right, it's not that easy. Right now, there are not really security tools that allow you to do this. So it's an open research problem. Actually, we are working on this at the moment. Yeah.
If I can just add, like, for example, like one of the Confucius one that we were explaining before, we were also starting to consider in that, like, with the input from the user. In theory, you have to consider it anyway, like, especially when you call like other contracts, like this is also considered as an input. So we started like somehow exploring that part of the state. But at the end of the day, it's like just that the input space is getting bigger and bigger, and you have to find like new heuristic, like in order like to explore it in a clever way. Because as we say, like doing a dumb fuzzer or anyway like a dumb automated test, it's easy. You just like put all the variables there and make a random combination. The whole point is to explore like this space in a clever way.
Any more physical questions? Okay, so the first question is, there are static dynamic analysis tools for most programming languages. What's different or novel or harder or easier with writing one for Solidity?
Yeah, so when writing one for Solidity, so yes, it's true, there are a lot of tools, but you cannot directly use them for smart contracts because, I mean, those tools were written for different architectures and different programming languages. You could use things like LLVM, so you could translate, people tried this, they failed to translate to LLVM, and then you could, this was the whole idea, and then you could use existing tools. But one of the challenges for Solidity in particular, or the Ethereum virtual machine, is this fact that it's stack-based, so you need to always consider that. And also that you have certain concepts, like Ether, like this environment variables, basically, block timestamp, block number. These are things that you don't really have in normal programs, or people that do not. Sure, I mean, in an operating system, you have syscalls, right? But like still, it's the idea behind it is similar, but you need to adapt basically. So these are the challenges, I would say. The fact that it's stack-based only, there are no registers at all, and yeah, actually, this makes it a little bit easier, in my opinion, to write a tool for it because you don't need to care about registers. Yeah.
Yep. And would your techniques improve on the state-of-art analysis tools for more general-purpose programming languages, such as Java and Go?
That's a very good question.
Yeah.
No, go ahead.
No, actually yes, because first of all, like what we talk about like today is like published work, so we hope that we improve the state of the art already. But if we want like to apply this like to other languages, we have to think like, for example, Confucius. There is like a huge like now fuzzing community that is working on fuzzing, and the way we actually manage like combined like the state exploration with the genetic algorithm. And also like the most novel part of that fuzzer is the read after write consideration in the whole like smartness, let's call that, of the fuzzer. That of course can be applied to other language, and we didn't when we developed like Confucius, we didn't see like anything like that like in the other I mean not in the other communities, but in the fuzzing community, so for other targets. So yeah, sure, like especially that work was not just like a translation of a fuzzer to the smart contracts, but was also like trying to find a new way to make it smarter. And I think I replied this one.
Okay. And is there any way for perhaps an online application or device to actually learn and detect the various different bugs?
So you have, if I understood correctly, the question the way is like, is there any online application that allows you to learn about smart contract bugs, how to detect them, how they look like? You have some CTFs that are online, so capture the flag things that you, I mean, with solutions already available. I don't know the name exactly anymore. Then you have these registry, of course, right, that Antonio just presented, this SWC registry. You have the top 10. I think consensus diligence. So one of security auditors, many companies that are available, they have this page, I think known security issues or something like that, that you can also read. So there is quite some material available already. So if you really are interested into this, yeah.
But if we talk about online application, like if the way I understood this question, like a web where you put your contract that they tell you if there is bugs or no bugs. I mean, I think there is something already around, like for some static analysis tool. But anyway, like at a certain level, I think you should not use like webs to submit like your code and then check for security. Just like install the tools on your laptop, at least.
Yeah. So like there's this famous IDE online in the browser called Remix for developing smart contracts, and they have actually, I think, a detection module that you can run on your code. But be aware that the code that you're implementing there, right, is going to be sent to a server. Potential, I don't know, or maybe it's run locally, I'm not sure, but like it could be. So if you're a company and this is one of your businesses, I wouldn't use those online portals, right? You want to actually use those tools offline.
Yeah. Last one.
Okay, last one. So how do you compare EVM-based and WebAssembly-based contracts? Which one is more secure?
Yeah, this is a tricky question. So it depends. So there are different ways so these WebAssembly contracts, there are different ways that these have been implemented. I know that, for example, Ethereum gave up. So Ethereum wanted in the beginning to have WebAssembly, EWASM, but they gave up on the idea. In terms of security, what is nice about WebAssembly is that I was talking about this LLVM stuff. So WebAssembly, the nice thing is the moment using WebAssembly, is easier to translate into this LLVM intermediate representation, and then you can run all these tools that are already available, right? So in terms of security, the moment you actually go from EVM to WebAssembly, it's much nicer because you already have a lot of tools available, okay? So in terms of security, it should be better, actually. Yeah, I know that Ethereum gave up on the WebAssembly stuff. They are now, the future is roll-ups, basically. Yeah. So they don't care anymore about the WebAssembly being, the Ethereum virtual machine bytecode being slow or not. This was one of the reasons. Yeah.
All right, I think that is the end of the questions. Thank you, Dr. Antonio. Thank you, Dr. Christof. Yeah, I think round of applause.